In example 4, we've got a random variable x which is normally distributed. And before I begin any normal question, I always write down what's the mean of the distribution, mu, so in this case it's 20. What's the variance of the distribution, which is this parameter here, so 9, and the standard deviation, which we're calling sigma, which is the square root of the variance, which is 3. So let's draw a little sketch of this distribution and work out what's going on here. So we know that the distribution is centered around 20 because that's the mean. And we've got some unknown value a. And this basically says the area to the left of a is 0.75 because we want the probability of x being less than a is 0.75. So because we know the probability to the left of 20 is 0.5, we know that a must be to the right of 20. We must have a there. And that's going to ensure that, well, we know this area here is 0.5 to the left of 20. So that means that this area here is allowed to be 0.75, this total area to the left of A. So we can use the inverse normal function on our calculator. So if we go to distribution, normal, and inv normal for inverse normal, what tail means is the area that we know, is it to the left of our unknown value or to the right of our unknown value? Well, in this example, it's to the left of our unknown value a. So we're going to put the tail as left. We're going to put the area as 0.75 because we know that that area that we've shaded in to the left of a is 0.75. And we're going to put our standard deviation, which is 3. Careful, it's not 3 squared, it's 3. And our mean is 20. So we get A is 22.023. And it's worth checking that we get an answer that makes sense. And this does make sense because it's to the right of 20. An alternative way of doing this would be to have said that the area to the right, this area here, is 0.25 because we know that the two areas have to add up to 1. So let's just check to see if we get the same answer. If we put right as 0.25, then we'd get exactly the same answer. So that gives us our value of A, 22.023. Let's have a look at B then. So we want the probability of x being greater than a to be 0.4. So let's draw a sketch again. In the middle we've got 20. And let's try and work out where a needs to be on our horizontal axis. So this says the probability, the area to the right of a is 0.4. So this probability to the right of 20 is a half. So we know that A, again, must be to the right of 20. Because if it was to the left of 20, then the area to the right of it would have to be more than a half. And we know that that area there is 0.4. So we're going to use our calculator and you're going to use tail is right because we know the area to the right of our unknown value is 0.4. So we're going to put area as 0.4. And we'll leave sigma and mu as they are because they haven't changed. And we get 20.760. And it's worth checking by using inverse cumulative to check that that makes sense. So if we put our lower as 20.760 and our upper as a really big number because we want all of this area to the right up to infinity, and just check that that does give us 0.4. Yeah, okay, so we've done that right. Part C is slightly more complicated. Let's draw out the distribution to try and work out what this area represents. So again, we've still got 20 as our mean in the middle of our distribution, and we're told that the probability of x being between 16 and a, so let's label 16 on our diagram, 16 up to some value a, and we know that area there is 0.3. Well, I don't actually know that a is to the left of 20 or to the right of 20. I don't know that yet, but we'll be able to confirm the fact that it is to the left of 20 in a second. Well, the problem is we can't use the inverse function on our calculator, the inverse normal function, because in order to use the inverse normal function on our calculator, we need to know the total probability to the left of a or the total probability to the right of a. And at the moment, I don't know the total probability because I don't know this part here. So let's work out what this probability here is to the left of 16, because then we will know the total probability to the left of our unknown value that we're trying to find. So we'll be able to use our calculator and the inverse normal function. So let's try and find out what that probability there is. So that's the probability that x is less than 16. So we're going to go to our calculator. We're going to put our lower as a really small number, like minus 9999. Upper as 16, because we want the area up to 16. And we'll leave sigma as 3 and mu as 20. And that probability there, that area, is 0.09121. Okay, so remember we did this because we wanted to know the total area to the left of our unknown value a. So now we can use the inverse function on our calculator to work out what that probability actually is, what that value of a is. So the total probability, if we add these two up, is 0.39121. So now we can use our inverse normal function on our calculator, and we're going to do the tail is the left, because we know the total probability to the left of our unknown value is 0.39121. So tail is left 0.39121, and that gives us 19.171. So A is 19.171. So that does confirm to us the fact that A is to the left of 20. I also could have told that because as soon as I knew my blue area was 0.09121, if I add on the area in between 16 and A, that total probability there is less than a half, which means that I have to be to the left of 20.